All right, so for today, we are going to be adding to your repertoire of derivative tools and ways that you can take derivatives and functions in particular that you can take the derivative of. Up here, you can see that we have the derivative of sine of x that we're going to be working on. The graph you're shown there is, of course, the graph of sine of x. And I want to start by just sketching out what would the derivative of that graph look like in order for us to be able to see what that derivative would actually be. Now, first of all, when we sketch the derivative from the graph, remember that I always like to start by looking for zeros. That is, places on the graph where the derivative would be 0, which means horizontal tangents. So you can see that happening every time it flattens out at one of the tops or bottoms. So each of those points is going to represent a derivative of 0. So I'm going to go ahead and start by just plotting each of those. All right, now I'm going to start looking to see what's happening between those zeros. All right, I'm just going to start by looking to see what's happening between these two zeros here. All right, so looking at the actual original graph there, is it increasing or decreasing? It's decreasing. Therefore, the derivative is negative. Because remember, derivative is slope. Decreasing, negative slope, negative derivative. And so that tells me that between those 2 points, those 2 zeros, I'm going to have to be going down to the negatives here. And I'm going to be doing something like that. All right, and then we look between the next set of zeros heading towards the right. Notice between those two, my graph is increasing in here. And since it's increasing, we're looking at a positive slope, and so we're going to be doing something like this. And we can keep following that same kind of pattern. So now we're back to decreasing. And so if I fill all of that in very roughly, I at least know the general shape of this graph. And yes, that graph should look a bit familiar. Notice that graph in red, our sketch of the derivative, looks a lot like cosine, doesn't it? And so it's looking like my derivative of sine of x is probably cosine of x, or in this case, theta. Now, a little detail-y stuff though, because I didn't actually calculate, for instance, what's the slope here at 0. I didn't actually calculate out that slope, but we could calculate it to know exactly how high that graph should go, to know what that slope actually is. If we calculate the slope at that point, you will find that it is exactly 1. Which means that actually this graph, the way I sketched it, actually going up to 1 and down to -1, is accurate. And so then we can conclude that the actual derivative, yes, is cosine of theta. No modifications necessary of that function. And once we know the derivative of sine of theta is cosine of theta, we could use that and the same techniques to figure out what the derivative of cosine is. And once we know what the derivative of cosine is, we can then go into the other trig functions, the secant, cosecant, tangent, cotangent, and we could use product rule, quotient rule to figure out all of those different results. Now, I'm not going to have us go through all of those to figure out what each of those is, but rather just give you now, for your notes, what each of the derivatives of the trigonometric functions are. So this needs to go into your notes, and then we are going to practice using these. All right, so here's our first practice problem of many that we're going to be going through here today. For each one, write down the original problem, and then we'll find the derivative of it and write down, of course, the derivative as we find that as well. All right, now, in this case, when I go to find f prime of x, I got tangent x over 5. Now, when I see that big old fraction, my mind starts going to quotient rule, right? So do we need to use quotient rule here? We actually don't need to. Now, can you? Yeah, technically you can, but there's a much simpler way to look at this. Because tangent of x over 5 is the same as 1/5 times tangent of x. And remember that anytime we multiply something by a constant like that, in order to find the derivative, really we can just do that same constant times the derivative of the function. So I'm going to be doing 1/5 times the derivative of tangent of x. What's the derivative of tangent of x? secant squared x. We got that just from our notes. You're going to be going to your notes a lot on these as you get to know these. All right. Now, that's fine as an answer. It is technically correct. But because the original was formatted with that over 5, it was given as the fraction, I do like to kind of match that formatting in my answer. So I'd actually answer it as secant squared x over 5. Both of them are technically correct, but I do like the latter just because it matches the first. But notice that when it's over a constant like that, you didn't need to use quotient rule. Now, if it's a function over a function, quotient rule. But function over constant, no. Next problem. Here we have f of x equals a negative cosecant of x. All right. In this one, am I going to need to use the product rule? No. Because it's a constant times a function. And again, anytime we have a constant times the function, it makes our lives a lot easier. So I know my answer is going to be negative 9 times whatever the derivative of my function is. So what is the derivative of cosecant of x? So you look in your notes, you find cosecant, and you see it ends up being negative cosecant of x times cotangent of x. And so that's what we're looking at there. So again, notice constant times a function. When I find derivative, it's the same constant times the derivative of the function. And so now I do want to simplify that down a little bit because you notice I got negative 9 times the negative trig functions. The negative times the negative is positive. So that ends up giving me 9 cosecant x, cotangent x. That's a little bit simpler. That's a good answer right there. Right, now for this function, when I go to find f prime of x, when I go to find the derivative, I have the square root of x times sine of x. By the way, when you wrote this down in your paper, make sure that you are super clear. That square root is only over the x. The line should not be extending over into the sine or anything like that, or it's going to give you the wrong impression. So I got two different functions being multiplied together here. This is where we do need to use product rule, because it's two different functions being multiplied. All right, so product rule time then. When I use product rule, remember, I'm thinking of it as two different functions that are being multiplied. Those are my two functions. And I need to do the derivative of one of them times the other original plus from there. So I'm going to start by doing the derivative of the square root of x. Now remember that square root of x is the same as x to the power of 1/2. And so when I then find the derivative of that, it ends up being 1/2 x to the negative 1/2. That's where we need to be at this point. You need to be able to turn the square root of x and find the derivative into that. But just to remind you, I could even clean that up a little bit more and be tidier with it and turn it into 1 over 2 root x. Same thing. But again, I only expect you to necessarily get it at this point, and so that's the derivative I'm going to use when I use my product rule here. So then I got 1/2 x to the negative 1/2. That's the derivative of the square root. And then that multiplies by the original function for the other part of it. So that's just sine of x. And then it's going to be plus. Now for the second part here, I switch which one I take the derivative of. So this time the square root of x is going to stay the same, but I find the derivative of sine of x. And what is the derivative of sine of x? Cosine x. Great. All right, so that is basic product rule. That's really our answer. Now, could we try to fool around with it and see if we could simplify it? Yeah, we can try lots of different things, but there's really not much we can do in order to simplify that down at all. So I'd be cool with this being your final answer. Now, the interesting thing about this problem, when having just done that last problem, is that that last problem ended up getting a lot bigger when we took the derivative. It ended up looking a little bit more complicated. This one actually ends up being not as complicated as even the last one was to find the derivative. Because remember that when we're doing subtraction or addition between them, that just means find the derivative of the first term, find the derivative of the second term, and we'll just subtract those two derivatives. So to find y prime here, I'm going to do first the derivative of the 2 secant x. And of course, the 2 just multiplies by whatever the derivative of secant of x is. And so the derivative of secant of x, go to your notes. Let's make sure you got those written down right. You should see secant x, tangent x. So that's the derivative of the first term. Then it's just minus now the derivative of cosecant of x. So now go and make sure that you got that written down. So derivative of cosecant of x, you should find that it is a negative cosecant x cotangent x. Now in this case, I would actually expect you to take it at least one step further in terms of the simplification though, because I have that minus and negative, so I'd at least like to see that cleaned up. All right, now for this one, when we go to find g prime of theta, notice we actually got a couple different function types involved this time. We're no longer just including the trigonometric functions. We have e to the theta, and then we have this tan theta minus theta. Those are going to be basically my two pieces of my function that I'm going to be looking at. And yes, they are multiplied, so I'm thinking product rule right now. So for product rule, I'm going to do the derivative of the first function. So the derivative of e to the theta. What is the derivative of e to the theta? E to the theta, yes. The fact that it's a theta doesn't change that. Theta is just working like x here. So it's the same rules as we had when we had e to the x. And then, so that's the derivative of e to the theta. So that multiplies by the other function exactly as it is, unchanged. So it's tan theta minus theta. Now that's going to be plus. Okay, now this one I switch which one I'm taking the derivative of. So I take the e to the theta just as it originally was, and I multiply that by the derivative of, in this case, what's in the parentheses, the tan theta minus theta. So first up in order to do that is we find the derivative of tan theta. What is the derivative of tan theta? Secant squared of theta. And then, what's the derivative of theta? Well, that's like saying, what's the derivative of x? Derivative of x is 1, so the derivative of theta is 1. And so, that is now the correct application of product rule, so that is our derivative. Now again, thinking about anything we can worry about simplifying or anything like that, there's maybe one thing we could simplify here, although it's not even necessarily simplifying, but I do want you to be aware of it just because sometimes being able to manipulate these things and change the way things appear could be good. Notice that really we have two terms here. We have one term and we have two terms. What do both of those terms have multiplied into them? E to the theta. Yep. So I actually, if I wanted to, I could actually rewrite this where I factor the e to the theta out of everything. And so it's equivalent to that. Now, do you have to go there? No. Did that even necessarily help us? Not necessarily. But it's good to see how we can manipulate these things, because at a certain point, it actually does end up being very useful to be able to do. It just depends on what we're given in the particular problem and what we're working with. All right, so once again, we have a mix of different function types. We have our trigonometric function mixed with an exponential again. Now, in this problem, I see a big fraction. That means division. So that means quotient rule in order to be able to find the derivative. All right, so finding f prime of t here. Quotient rule now. Do you have quotient rule memorized? If not, be working on it and practicing it so that by the time we get to our next test that you will have it memorized. All right, so let's check. The way that we remembered it, one way at least, low d high first. So low, that means take the lower part of the fraction, e to the t exactly as it is, times d high. D high means the derivative of the top of the fraction, so that means derivative of cotangent of t. The derivative of cotangent of t, we can look that up. We see that it is a negative cosecant squared of t. All right, then minus. We just did low d high, so the next step is high d low. So high means cotangent of t. And then times the derivative of the bottom of the fraction. So the derivative of e of t, of course, is e to the t. I'm just going to put parentheses around that to keep it all separated and clear about what is where. And then that is all over the square of what's below. So that is e to the t squared. All right, and we have now successfully found the derivative using the quotient rule. But I don't actually want us to stop here on this one. Yes, you can technically stop here, and this is where I need you to be by the end of the class today. But moving forward, by the time we practice these a lot, we should be at the point where we can focus on cleaning it up, and this one can get cleaned up a bit. Do you see how this fraction here actually will reduce? How it will simplify? What can I cancel out of every single term on both the top and the bottom? E to the t, yeah. Because you'll notice there's one in the first term on the top and the second term on the top. That must be the case in order for us to be able to do that. And on the bottom, we have e to the t squared. Now I can't cancel out all e to the t's on the bottom, but I can cancel out one of them, which means it's no longer going to be squared on the bottom. There's just one of those e to the t's left. So if I do that now, that leaves me with negative cosecant squared t minus cotangent of t all over e to the t. It's not quite as ugly or scary looking as what we found on the first level. It's a little bit simpler to work with. We don't have to do e to the t nearly as many times now. Still not super easy or super pretty, but it's at least better. The nice thing about having done this is that if we were being asked to now find the value, like if we were told, okay, now figure out what's the value of the derivative when t equals 3. Or more interestingly, since we're dealing with trig functions, what if t equaled pi? It's nice to not have to do e to the power of that number quite so many times. A lot less probability that we're going to make a mistake somewhere along the line as well. All right. Next problem. Let's find the derivative of cosine theta sine theta. All right, now in this situation, I know I'm looking to find the derivative, so I'm going to end up with a y prime equals here. And I got cosine theta times sine theta. Yes, I am going to need to use product rule here. And so, let's go ahead and start applying product rule. First up, I'm going to do the derivative of cosine of theta. And the derivative of cosine is negative sine. So that's going to be negative sine theta times sine theta. So that's the derivative of the first part times the second part left as it was. All right, then it's plus. Now I do the derivative of the other one. So the cosine of theta is going to stay cosine of theta. And I do the derivative of sine theta, which is also cosine theta. Now in this case, can I clean it up? A little bit. I don't really like leaving it in terms of sine times sine. We can actually turn that into a negative sine squared of theta. Plus, and then again, cosine times itself is going to be cosine squared. So I'm going to write that as cosine squared theta. Now, can that simplify it all? No, it's close to something that could be simplified a little bit, but no, that cannot be simplified from there, so final answer. All right, so for this one, as I take a look at the original setup, when I go to find the derivative here, I'm thinking quotient rule, because I'm saying a function divided by a function here. All right, so for quotient rule, I'm going to be doing low, 1 minus sine x, d high, so that's the derivative of cosine of x, which is a negative sine of x, minus high cosine of x, d low. Now the derivative of 1 minus sine of x, the derivative of 1, of course, is 0, so that part goes away. So now I'm doing the derivative of a negative sine of x, so negative cosine of x. All right, and then that's all over the square of what's below. Well, that means 1 minus sine of x squared. Now, coming out of today's new lesson, you should be able to give me this, no problem. Now, we can simplify it a little bit. This is where we start pushing into, okay, now if you're really getting things well, you can do this part. I want to simplify, which means I'm going to actually do the multiplication parts on the top. All right, so cleanup time here. I'm going to multiply through, so the 1 times negative sine of x gives me negative sine of x. And then that's minus sine of x times negative sine of x, so that's going to become plus sine squared of x. All right, now it's minus cosine times negative cosine. Well, that'd be minus a negative, so that's going to be plus cosine squared of x. All right, and then that's all over still the same thing. I'm just going to leave that as it is, 1 minus sine of x squared. All right, so that's another basic level of cleanup. Again, I would expect you to be able to get to this coming out of today's lesson, just saying, okay, all I'm doing is multiplying things together. Now, the question, though, is do we have to? Well, I would say that if you stopped here, no, that wouldn't necessarily accomplish as much for you. However, I'm not going to stop there because I remember at least 1 or 2 of my trig identities. Even if I forget all of them, there's at least one that comes up often enough that it's really useful. What does sine squared plus cosine squared equal? Sine squared plus cosine squared equals 1. That's why I like that one. It works out so simply. All right, so then I'm going to go ahead and do that. I'm going to turn this into, well, the negative sine of x is still there. Okay, so negative sine of x plus 1. All over still 1 minus sine of x squared. That certainly made things a lot simpler. Although we can even go simpler than that. Can you see how? Well, what if I change the way I wrote the top? What if instead of starting with the negative, what if I started with the positive on the top and wrote it as 1 minus sine of x? Now do you see how we can reduce it a little bit further? You notice on both the top and bottom, because inside the parentheses on the bottom I have 1 minus sine of x, I can cancel out that whole chunk, 1 minus sine of x. And so the whole thing boils down to y prime equals 1 over 1 minus sine of x. Yes, there still is a 1 minus sine of x on the bottom because, remember, it was squared, so I could cancel out one of them, but I couldn't cancel out both. And so when you start feeling more and more comfortable with doing the derivatives of these, then you start pushing yourself into saying, okay, now how can I really get into something much simpler as an answer? And certainly that would be a lot easier to work with than what we started with.